Okay, this is just a short little example of how a DC motor works and some of the constants and derivations I used in MATLAB to start my project. First off, I just want to explain sort of how the DC motor works, and this is how it looks. And the stator, it provides a constant magnetic field, and the armature, which is the rotating part, it provides it just consists of a simple coil. The armature is connected to a DC power source by a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil starts to rotate. You can see that right here. And as the coil rotates, the commutator rings connected with the power source are of opposite polarity, so as a result, the left side of the coil, electricity will always flow away, while electricity on the right side will always flow towards. And you can see here they have this one, but you can add another loop and more to like balance the spinning motion of the rotor out, because if you just have two, then there's a negative or a zero torque at the top, and then it almost creates like a static or like a small oscillation in the DC motor. So adding more always has that spinning motor force. So, and it smooths the operation of the motor down. And the transfer function is defined as the ratio of the Laplace transform of the output variable to the Laplace transform of the input variable. The DC motor converts electrical energy into mechanical energy, and the electrical energy supplied at the armature terminals is converted into the mechanical energy. And this is just the circuit with a DC motor in it, and that's, you can see the rotor and the torque angle. And these are some constants, or not all of them, but symbols and the variables and how they were used in MATLAB. So the moment of inertia of the rotor was J, and it's assumed to be 0.01, and then those units. And then the motor viscous friction constant will be B. The electromotive force constant will be Ke. The motor torque constant will be Kt. R will be this electrical resistance, and L will be electrical inductance. And in general, the torque generated by a DC motor is proportional to the armature current and to the strength of the magnetic field. In this example, we show, or the example right here, that's this circuit with this DC motor in it. So this kind of only pertains to this circumstance right here. We assume that the magnetic field is constant, and so therefore the motor torque is proportional to only the armature current, which is denoted by the I and by the constant factor Kt. So this DC motor is referred to as an armature controlled motor. And another thing that has to be taken into consideration is the back EMF, which is E, and it's proportional to the angular velocity of the shaft by a constant factor Ke, and that's this equation right here. And then we got the transfer function. We applied the Laplace transform on the above equations, and that's how we got the JS plus B equation. And then the state space model derivation. These are just some of the preliminary equations that are going to be used for MATLAB and for finding the Bode plot and further designing of and modeling of the DC controller. And this is the state space algorithm. And it all takes into account the previous equations that I have up here. And there's a few design requirements that you're trying to go for, rather, I guess. And basically, assuming that the motor rotates at 0.1 radians per second in steady state for an input voltage of just 1 volt, and then we want the motor to rotate at that desired speed. We will require the steady state error of the motor to be less than 1%. So another performance requirement for the motor is that it must accelerate to its steady state speed as soon as it turns on. So we don't want any kind of lag or delay there. And so we want to have a setting time less than 2 seconds. Also, the speed, since it's faster than the reference, we don't want to damage any equipment or have any kind of damage to the motor. So we want to have a step response and an overshoot of less than 5%. And that's what we have in here. So that's what we're shooting for in MATLAB. And we can also derive the transfer function in MATLAB, and that's what's down here in terms of S. And here, what we have is a model for that's why the +1 is in the bottom from that up there in terms of that. And I really hope the sound didn't just get cut out, but and then the rest will be done with MATLAB and modeled and ready to present on the 10th.